Today, I'll introduce a very exciting software we are developing with my coworkers, Dr. Hao Wang and Dr. Paul Lucy. So this will be a real-time lunar surface mineral and magnesium number mapping tool using machine learning. So we've already collected a lot of awesome lunar samples. From the near side, we have the 3 lunar missions, 6 Apollo missions, and the Chang'e 5 mission. And from the far side, we have this exciting, successful sample collection by the Chang'e 6 mission from the Apollo basin. And in the near future, we'll have the Artemis 3, which will return sample from the South Pole Aitken near the South Pole. So we've learned so many knowledge from the current sample return. They've played a very important role in understanding the lunar thermal history and the evolution progress of the moon. But still, we need more because currently, for example, the mantle composition at a global moon is still sort of unclear. And to learn this information, a good sample collection will be if we can get some sample from those basin rings or central peaks, those will be great for helping us to understand more about mantle composition and deep crustal composition. Although these basin rings and central peaks will be high hills and massifs, which will be hard to reach. But what we can do is to take some of the mass listing of the massifs. For example, here I have a picture showing the central peak of Copernicus, and you can see that there are tons of rocks falling off from the central peak, and some of these rocks may be from the mantle because the Copernicus crater is located near the ring of the Imbrium basin. And also we can collect some of the ejecta, the craters, which may contain mantle material. And one of the most interesting sites will be the South Pole Aitken Basin, because this area has the thinnest crust of the moon, and it has been shown, like by many studies, this area have exposed lots of mantle material, both near the rim and also within the basin. For example, this will be the also pyroxenite or also pyroxene-rich sites identified within the South Pole Aitken by Yamamoto et al. Then I'd like to introduce a little bit of the algorithm we're using to map the magnesium number and mineral. So for example, we use this, we were applying this to the moon mineralogy mapper dataset. We applied a sensitivity test by adding noise to the spectra by 10,000 times. Then we derived a histogram of the derived magnesium number and mineralogy for these noisy spectra. And we can see that the magnesium number, even at high magnesium number, where the absorption feature will be a little bit weaker, then we can still get a pretty precise estimation on the magnesium number and minerals. Our overall accuracy for estimating magnesium number is around 5. And for plagioclase will be within 5 volume%. And for olivine and pyroxenes will be within 4 volume%. And here's some validation toward the model. We used both the LCC lunar soils and LP data. So for the LCC lunar soils, they use 90 soils, and the correlation to the minerals is almost near 1, which is a great correlation. But the magnesium number estimation a little bit high, it's around 10. But this is because the LCC soils have a very narrow range in magnesium number variation. So we applied our algorithm to the moon mineralogy mapper data, and on a global scale, we resampled the map to the 2 degree per pixel lunar perspective resolution. And on the left bottom is our mapping result, and on the right, his histogram shows a value comparison with the lunar perspective result, where the black is from lunar perspective, and our work will be kind of discrete because it's limited to the data and the CPU of the computer. And we can see the correlation between our data, and the LP is great, which both have the same peak and distribution along the entire value range. So here's some result we used to map the lunar south pole. We derived this magnesium number map around the entire South Pole Aitken. We can see that the Mare and Crypto Maria regions will show much lower magnesium number value, whereas the rim and ejecta will be much higher in magnesium number. And also we identified areas having also pyroxenite, this magnesium number higher than 85, which might be mantle candidate materials exposed in the South Pole Aitken. And here, those red dots are the identified orthopyroxenite at Apollo Basin and Schrodinger Basin. The Chang'e 6 landing site is indicated by this gold star at the Apollo Basin, and you can see it's surrounded by several mantle candidate sites. And this area might contain ejecta from Chaffee S or those ejecta from the little crater on the right and some ejecta from the South Rim. And possibly this this mission may return the very first unambiguous mantle material. So then we adapt the algorithm to machine learning, which is capable of processing a large amount of data in a shorter time. And this shorter time will allow us to do a real-time surface magnesium number and mineral mapping for both robotic and manned surface sample collection. So applied some preliminary simulations. This work was done by my co-author, Dr. Hao Wang, and she used a Spectra data set that contains 250,000 data points. And she applied a spectral match using machine learning and compared to my spectral match using IDO in my laptop, my spectral match take 13 seconds, which is pretty quick to my idea. But using machine learning, she could run it to within 0.1 second, which is like a snap. It's really fast. And this very fast spectral matching can help us to realize the real-time mineralogy and magnesium number mapping on surface. And here is a schematic diagram. Imagine you are working on the surface as long as you have a spectrometer attached either to your astronaut, a spacesuit, or a lander or a rover. You can just do a quick scan of the local area with the software, then you can very quickly find the materials that you are mostly interested at. For example, if you're in the South Pole Aitken, you can quickly find which material has the highest magnesium number and the highest orthopyroxene content, or which one has the highest olivine content. And this will add a lot of accuracy in sample collection for both manned and robotic sample collection.
Sorry to interrupt you, about 1 minute left.
Oh, I'm done. Thank you.
Oh, perfect.
One quick question.
Can I take that?
Yeah.
So just to clarify, the training data set in machine learning is already modeled mineral spectra, right? But isn't that cheating in a way? You're like modeling spectra and then like feeding it to a model to a mathematical to like decode mathematics, but that's not how real spectra works. Model spectra is like the most perfect case.
Yeah, so because this is just a preliminary test on the algorithm, right? So in the future, we'll add noise like we did to a noise, we'll add a noise that level that's equivalent to remote sensing data, or I will test some, collect some data in the field and train this model so it can perform better with noisy data.
Thank you.
Okay. Right, with that, we will seamlessly transition to the geophysics portion of the show. And our next speaker is Jingshuan Huang, We'll be talking about seismic detection of shallow tubes and voids, a feasibility study based on 2D and 3D modeling.
Yes, the worn down button is the board.